Hello everybody, I'm starting the discussion with the Charpits method, and this Charpits method has actually four different type of standard with standard forms, out of which one is the separable equations. So let's start the class, the Charpits method. Over here, we generally deal with nonlinear first order partial differential equation. This kind of nonlinear first order partial differential equation. Hmm? And the basic idea of Charpit's method is to introduce a second partial differential equation of first order like this, such that these two equations f and g are compatible to each other. Compatible, what is the meaning of compatible equations? I told you the last lecture that compatible means that both of these two partial differential equations will have a single solution. Okay, in that sense we say that these two partial differential equations are compatible partial differential equation or compatible PDE. And if it is possible to find out a second PDE, in that case you see over here the first partial differential equation and the second partial differential equation. Both of these two partial differential equations, although they are nonlinear, but both of these two partial differential equations involve two unknown parameters. One is the parameter p, that is actually del z del x, and another is the parameter q. So p means del z del x and q means del z del y. All right. So over here, these two quantities, these two differential equations p involve two unknown quantities p and q, and as because we have two differential equations, then we can theoretically solve them at least and find the expressions of p and q in terms of these x, y, and z. And that's why this is the reason we need a second partial differential equation. Now, how can we construct this partial differential equation? I am coming later on about the construction of this partial differential equation. But if it is possible to find the expressions of p and q, then from in this relation dz, we know that this dz, this differential dz is equal to del z del x into dx plus del z del y into dy. So this del z del x, that is the expression of p. So over here we put this expression of p, and del z del y, this one is del z del y, that would be the expression of q. So this is the expression of q. So we have this type of relation that dz is equal to p into dx plus q into dy. All right. So if it is possible to find the expressions of p and q, then we can put these expressions of p and q, and then we can integrate it, and we will get the solution, that is z in terms of x and y. That would be certain functions of x and y. And of course it would involve after integration, it would involve certain parameter, maybe an arbitrary constant small a. And in this way we will be able to find out the complete integral of this given differential equation. This is the given differential equation, small f of x, y, z, comma p, q is equal to 0. Alright, so this is the basic idea of Charpit's method. But although the idea is simple, but computation is a little bit complicated over here. Because we need to find out a second partial differential equation g of xyz comma pq, p comma q is equal to 0. And I told you that this G is to be found such that this F and G will be compatible. What was the necessary and sufficient condition of compatibility? I told you earlier that this is the necessary and sufficient condition for compatibility of the partial differential equations. F is equal to 0 and G is equal to 0. So this compatibility condition has to be satisfied, and if we expand this Jacobians, in that case, after expansion, we can express the entire expression as a partial differential equation involving G. You see, these are the partial derivatives of G: del G del X, del G del Y, then del G del Z, del G del P, and then del G del Q. So we actually have a partial differential equation involving this quantity G, and this is a linear partial differential equation. Linear, why? Because you see, this the derivatives del G del X, del G del Y, del G del Z, then del G del P, del G del Q. The power of these derivatives are all equal to 1. And these are the coefficients. Okay. So we can at least theoretically find out the corresponding Lagrange's auxiliary equation, and these are the Lagrange's auxiliary equation: differential dx divided by this coefficient of del g del x, that is actually our f suffix p, or partial derivative fp. Similarly, differential dy divided by this coefficient fq, partial derivative fq, and so on. We can consider this coefficient, then we have the differential dz by this expression. We can consider this coefficient, then differential dp divided by this expression. We can consider this coefficient as well, del g del q. Then we will have differential dq divided by this coefficient of del g del q. So in this way, we can find the corresponding Lagrange's auxiliary equation, and we can integrate them. And ultimately we will be able to find out the this second differential equation g of x y z p comma q. Okay, that is equal to 0. And remember, over here all this ratio, we will have to choose the simplest ratio in order to compute the expression of g. We will have to choose the simplest expression out of this 5 ratio in order to compute the expression of g. Just we need certain expression involving p and q, that we need to remember in our mind. That's why all this ratio may not be useful. So don't be afraid about this kind of complicated expression. We might have 5 different ratio, and remember, we just need to find out some expression involving p and q, so that we can solve, we can have this kind of second relation involving p and q, and first relation was given as a question, and we can then solve these two relation and find the expression of p and expression of q. Got it? So that is the basic idea. So remember that these 5 expressions, all these 5 ratio may not be useful in the computation of the second relation involving p and q. It is particularly mentioned over here. You can see that it may be noted that all the Charpit's equation, these equations are called Charpit's equation, all the Charpit's equation need not be used. We will have to find out the simplest of all these solutions. Let us discuss an example out of from this portion. You see, this is a nonlinear differential equation. P square plus q square into y, that is equal to qz. So if we shift this qz on the left hand side, we will have this kind of differential equation. That will be the expression of f. F is equal to p square plus q square into q minus into y minus qz. So p square plus q square into y minus qz is equal to 0. That would be the first differential equation. So in order to compute this Charpit's equation, we just compute all these expressions in the denominator. So we compute these partial derivatives, and after computation these partial derivatives, we put all these partial derivatives in this equation, and we got this kind of equation. And in these two equations, we will have to choose the simplest relation involving P and Q. Okay. So if you consider the last two ratio, this last two ratio, then you see over here this q square will get cancelled with this q square. So we will have dp divided by pq. On the right hand side, we will have dq divided by minus p square. And again, over here we can cancel one p. So we will have this type of expression: p dp plus q dq is equal to 0. And on integration, we will have this type of relation: p square plus q square is equal to some constant a. All right. So this is the second relation involving p and q, or this expression g. Okay. Although we say that g is actually a function of x, y, and z, this may involve these quantities x, y, and z, but they would involve this p and q. Okay, so in this fashion, we get the second relation involving p and q. And we already in this question we have a relation involving p and q over here in this given question. So now we need to solve these two equations. This is equation number 1 and this is equation number 3. We will have to solve these two equations, equation number 1 and 3. You see in this expression it's a bit easy, because p square plus q square is equal to a. So we can put p square plus q square is equal to a over here, and then afterwards we can find the expression of q. Q would be is equal to a y divided by z. So in this way we will be able to find out the expression of q, and after computing the expression of q and putting this expression of q over here, we can find out the expression of p. All right. So we shall have actually two expressions, plus and minus. Plus minus with power of a minus q square. This is the expression of q. Ay divided by z. This is the expression of q. Okay. Although we can simply choose this positive symbol or negative symbol, whatever you wish. Just we need one expression of p and one expression of q. So we got one expression of p and one expression of q, and we now put these expressions of p and q in this relation. Dz is equal to p dx plus q dy. So we just put these relations of p and q over here in this relation, and afterwards that might be a bit difficult to integrate, but if it is possible to integrate, then only we will be able to compute the total the complete solution of this integral. So after this kind of manipulation, might be a bit difficult, because these are all nonlinear differential equations. And remember that all the nonlinear differential equations cannot be integrated. That is the sole theory that you need to remember. All the nonlinear equations cannot be integrated. You will be provided only those category of differential equations which can be integrated. Okay. So most of the differential equations most of these nonlinear differential equations cannot be integrated by this kind of traditional techniques. In that case, we will have to follow certain numerical procedure to compute the solution of this kind of partial differential equation. Then we will have some numerical solution. But over here, analytically, the given equations will be in the form of integrable function. And so we just over here integrate it, and due to integration, 1 second partial 1 second parameter or arbitrary constant would appear. So finally, by simplification, we get this type of complete integral involving the two unknown parameters, small a and small b, or two arbitrary constants, small a and small b. So this is the technique of computing complete integral by the Charpit's method. Okay. So this is one example, and there are several other examples have been provided in this book. You can go through these examples as well. Some other examples are also there. You can go through these examples. Let's start this second part. That is this. Let's start the different category of different types of equations that to be solved by Charpit's method, and we mainly categorize them into four categories. We call them type 1, type 2, type 3, type 4. So the first type of equation that we generally deal over here is this kind of differential equation involving only the partial derivatives p and q. Partial derivative p means this del z del x, and partial derivative q means this del z del y. Okay, so involving these two quantities, sometimes we are given a partial differential equation, and if a partial differential equation involves only these two quantities, they may be linear, nonlinear, whatever it is, but it can be proved that the solution of the partial differential equation can be written in this form: z is equal to x plus by plus c, not this 0. Okay, this is a printing mistake. Forget this 0, not this 0. 0 would not appear over here. So z is equal to ax plus by plus c would be a solution to this kind of partial differential equation, and this is a trial solution. Mind it. What is the parameter small a and b? I shall discuss them. Actually, there is only one parameter, and the second parameter will be dependent on the first parameter. If you consider z is equal to ax plus by plus c, then you see if we differentiate this relation with respect partially with respect to x, we will get this kind of relation. Del z del x is equal to a. We will get this type of relation. Del z del x is equal to a. Similarly, if you differentiate it with respect to y, you will get this type of relation. Del z del y is equal to b. What is del z del x? Del z del x is equal to p, and del z del y is equal to q. Okay. Now, as because a relation involving p and q is provided in terms of this partial differential equation, so we can now put these expressions of p and q in this given partial differential. So we will have this type of relation: f of a comma b is equal to 0. Okay, you see, we will have this type of relation: f of a comma b is equal to 0, and this is a nonlinear relation involving a and b. And if we theoretically, at least, we can write this expression in this form: b is equal to phi of a. B can be expressed as certain function of a. Alright, b can be expressed as a certain function of a, and therefore z is equal to ax plus, in place of b we can put phi of a into y plus an arbitrary constant c. So over here, this would be the complete integral of the given partial differential equation. So over here, we just need to solve this kind of partial differential equation. Or this is not a partial differential equation. You see, this is in place of whenever p and q are replaced by a and b, this will be an algebraic equation. Just maybe this kind of equation, maybe this kind of equation: a square plus b square maybe is equal to, say, 1. In that case, you can easily find out the one expression: b is equal to, maybe you can consider plus minus. I'm not considering the plus minus, I'm considering only one term of b. B is equal to 1 minus root over of 1 minus x. So that would be actually our function phi of a. So in this fashion, you can compute the expression of b and put it over here. So you can observe that over here we have only two unknown parameters. This is one unknown parameter and this is another unknown parameter. Although in the model ax plus by plus c, we had three unknown parameters, but over here actually we have two unknown parameters. This is the first unknown parameter small a and the second unknown parameter is small c. So in this way you can find out the complete figure of the even partial differential equation. You can consider this kind of example. Over here this is the trial solution. So over here p is equal to a, hmm, and q is equal to b. So you put these expressions over here, and finally you will give the relation that b is equal to 1 minus root over of a whole square. So in this solution we just put the expression of b. So this is the final solution of the given partial differential equation. And you see, in these are very easy kind category of partial differential equations, very easy to solve, and just you require only 2 minutes to solve this kind of partial differential equations. And this kind of differential equations are sometimes selected in competitive exams, which can be solved within 2 or 3 minutes. You can go through few other examples as well. Now we consider this second type of partial differential equation. In this second type of partial differential equation, the independent variables are absent over here. That means the variable x and the variable y. These two variables are absent over here. F of z comma p comma q is equal to 0. This is the second type of partial differential equation. We need to solve this kind of partial differential equation. And you see there is a small mistake in the book regarding the notation. What we actually do, we actually consider that z is some function of this kind of expression x plus ay, where a is an arbitrary constant. So what we expect that z should be some function, maybe psi of x plus ay, x plus ay, maybe psi of x plus ay is x plus ay, this kind of expression. But the problem in this book is that they have used the same notation as the partial differential equation A. So over here I am changing this notation. In place of A, I am writing psi of u. Okay, so I am assuming, although this is just a notation, it doesn't matter, some function of u. What is u? U is equal to this x plus ay. So over here it would be some function of x plus ay. These are the small mistakes that have been there in this book. Anyway, I have any option to change all these results. This much I can do, that z can be considered as some function of u. Now if it is now further differentiated, if this kind of relation is further differentiated with respect to x and with respect to y. Let us first differentiate this relation with respect to x. Then what we shall have? We shall have this type of relation, del z del x. That is actually our small p. Del z del x. Del z del x means we will have to differentiate this function with respect to u, and then u is to be differentiated with respect to x partially. So what we shall write over here, we should write it in this fashion. That would be dz du multiplied by u is to be differentiated with respect to x. So we should write del u del x, and that would be is equal to simply dz du multiplied by this expression. Whenever u is differentiated with respect to x, we will have only 1. So we can drop this one, and ultimately we will have e is equal to z du. So you see, it doesn't matter whether you choose this expression as a function f or the function psi. It doesn't matter. Ultimately, we will have this type of relation. E is equal to dz du. Okay. Similarly, whenever we differentiate this relation with respect to y, okay, now whenever we differentiate this relation with respect to y, in that case you see q will be is equal to del z del y, and that quantity del z del y can be written as dz du multiplied by del u, sorry, del u del y. Okay, and this dz du remains there. So this dz du is there, multiplied by whenever this u is differentiated partially with respect to y, we will have small a. So this is the relation q is equal to a into dz du. All right. Now we are given that we are given this differential equation f of p, q, and z. So z was there, p was there, and q was there. That was equal to 0. So we can now put this expression of p over here and this expression of q over here. We will have this type of relation, and then afterwards we can solve this relation. We can find the expression of dz du. We can find some expression of dz du, maybe, and that would involve the remaining expressions, that is z and a. So it would be certain function of z and a, like this. And afterwards you see dz by phi function, phi of z comma a, that would be is equal to du, and we can integrate it, and we will be able to find out the final solution. The corresponding integral is represented by capital E. So this is the basic blueprint of finding the solution of this kind of partial differential equation in type 2. You see, this is a partial differential equation involving p, q, and z. So we assume that z is certain function of u, and we can directly write p is equal to dz du and q is equal to a into dz du. In competitive exams, at least, you don't have to show all the deductions. You can directly write p is equal to dz du and q is equal to a into dz du. But in your final examination of BSc course, you please write the entire expression over here, that how did you get these results. Although these are very elementary and easy, but please write all these exams, all these results in your final examination. Okay. Anyway, so now you can put this expression of q, p over here, and the expression of q over here, and over here. And we will have this type of relation, and then we can solve this relation and we can compute the expression of dz du. All right, so we get this kind of easy expression of dz du. A into dz du is equal to this, and then divide the left hand side by dz du and multiply it by du. We will have this type of expression. So divide it by z minus a, az minus a, and multiply this expression by du. So we will have this kind of simple expression, and then integrate it. We will get this kind of equation where small a and small c, these are two unknown parameters or arbitrary coefficients. So in this way, we can find out the complete integral of this kind of given differential equation in type 2. There are certain other examples as well. You can go through these examples. Now, the type 3 category of differential equation, that is called separable equations. Particularly, this separable equation is explicitly included in your syllabus. What is separable equation? We say that the equations are separable whenever, first of all, the dependent variable z is absent. Hmm. Dependent variable z is absent, and the given equation after certain manipulation can be expressed in this category of form, where on the left hand side this f is a function of x and p. P means the partial derivative del z del x, and the right hand side would be another function involving y and the partial derivative q. Q means del z del y. Then only we call it separable. Separable in the sense that we can separate these two expressions. Some expression involving x and p, and some expression involving y and p. That this kind of forms are called separable forms. And we can that is actually an assumption. We assume, you can say, how can we assume this kind of assumption? You can say that this is a trial solution. We can assume this one. If we get certain solution, then we can say that our assumption is correct, otherwise the assumption is incorrect. So we assume that this left hand side and right hand side, both of them are equal to certain constant. It may be variable quantities, but that is our assumption, that both of them are equal to certain constant. And what is the value of that constant? Let us call it small a be the value of this kind of constant. Apparently, it may appear that the left hand side and right hand side, the expression of left hand side and the right hand side should vary depending upon the values of x, y, p, and q. But we assume that no, this value of left hand side and right hand side are not varying at all. We assume that this is a constant quantity. And what is the value of this constant? We suppose that this constant is equal to a, small a. So first of all, we can consider the left hand side. If this left hand side f of x comma p is equal to small a, and from this relation we can find this function p that may be represented as a function of x and a. Got it? Similarly, if you consider the second relation, capital F of y comma q is equal to this small a, then from this relation we can compute this expression q as a function of y and small a. And as because we got the expressions of p and q, therefore this in this relation dz, that is equal to p into dx plus q into dy. In this relation dy, in this relation we can put these expressions of p and expression of q, and afterwards we can integrate it, or we can convert it into certain form which will be easy to integrate. And if it is possible, or if it is easy to integrate, then only we can proceed. Okay, so over here we will have this type of relation. This is the expression of p, this is the expression of q, and afterwards after integration we will have this kind of certain solution of the given partial differential equation in separable form. So let's discuss an example over here. This is a given differential equation. Now you see, in this differential equation, if we divide this total differential equation by y and then by x square, so by cross multiplication, this x square will come over here and this y will come over here. So now if we look at this expression on the left hand side, this is an expression involving p and x, and this is an expression involving q and y. We assume that this value is equal to some constant a. So if we consider the second ratio, q by y is equal to a, Then from that ratio we can compute the expression of q is equal to ky. Similarly, if you consider this expression to be equal to a, then from this relation we can find plus minus p is equal to plus minus of this kind of expression. Hmm. But just we need one expression of p, so we choose this positive expression. So we got p is equal to this type of expression root over of a into x divided by root over of 1 plus x square, and q is equal to a into y. Now in this relation dz is equal to p dx plus q dy. In this relation we just put the expressions of p and q, and afterwards we have this type of result, and then we integrate it. Luckily this is easy to integrate. If it is not so much easy, then it would not be possible to integrate it. Anyway, so after integration we get this type of relation, this type of solution. There an arbitrary constant small a and another arbitrary constant small b is there, so it gives us the complete integral of a differential equation which is separable. Okay. So this is an example of a complete of a partial differential equation, solution of partial differential equation in separable form. Again, this kind of differential equations are also in separable form, so we can continue this kind of differential equation and find the solution of the complete integral of this kind of partial differential equation. And the last category is very much easy, that is in Clairaut's form. Where if a differential equation is given in this standard form, z is equal to px plus qy plus f of p comma q is equal to 0. You can recall that in ordinary differential equation as well, you got this kind of equation in Clairaut's form. There we had y is equal to some p into x plus certain function f of p. In case of ordinary differential equation, where p represents dy dx in case of ordinary differential equation. Now similarly, similar to this p, we have this term px, and similarly we have another term qy in case of ordinary differential equation, where z is actually dependent on the independent variables x and y. Therefore, for these two independent variables, we have the terms px and qy. And similar to this kind of expression f of p comma q, we have the expression f of p comma q just similar to f of p. So this is the Clairaut's form as you got in case of ordinary differential equation. And the corresponding Charpit's equation can be written in this way. And in this Charpit's equation, you can observe this last two ratio. This last two ratio will be in the form that dp divided by 0, that is actually dq divided by 0. So whatever expression it is, that may be certain, maybe dt or whatever it is, then dp will always be equal to 0. dp will always be equal to 0, and therefore from this relation we can say that p is equal to some constant, maybe small a. Similarly, from this ratio dq by 0 is equal to dt, you observe that dq will always be equal to 0, and then therefore q must be is equal to some other kind of constant b, and therefore we will have this final result that p is equal to a and q is equal to b. So over here p is equal to a and q is equal to b. We get this type of results, and if we put these expressions of p and q in this given differential equation in Clairaut's form, we will have this kind of solution: z is equal to ax plus by plus f of a comma b, involving the unknown parameters a and b. So in this way we can find the solution of the differential equation in Clairaut's form. over here this is a differential equation in Clairaut's form, so we can directly put P is equal to A and Q is equal to B. Of course, there you will have to state that we assume this kind of we assume a solution, or you will have to state that the corresponding Charpit's equation are this, and from this Charpit's equation you get this kind of relation: P is equal to A and Q is equal to. You please do not put directly P is equal to A and Q is equal to P. Try to justify how did you get this relation P is equal to A and Q is equal to B. Okay, so in Clairaut's equation, from this Charpit's equation, you can get this relation P is equal to A and Q is equal to B, and thereafter putting P is equal to A and Q is equal to B, you will be able to find out the solution of this differential equation. Okay, so these are the technique of solving the different kind of standard forms of type 1, type 2, type 3, type 4 category of Charpits of differential equation using this Charpits method. Especially the third category of equation, that is separable equations, are included in your syllabus. And regarding the questions in your competitive exam, you can go through this exercise. You see at the end of this exercise, there are certain examples, say this kind of examples. Find the complete integral of this kind of equation: p square plus q square is equal to x, that is equal to p into z. That is in category 3. Sorry, category 2, type 2 partial differential equation. Type 2, the partial differential equation involving p, q, and z. So there you can solve these differential equations. That has been selected in GATE, although it was long back, but afterwards these different kind of questions have been selected in GATE examination. You can go through the syllabus of GATE examination. And there are some other examples. These examples, these are from different GATE examinations. So you can solve this kind of problems. You see, these are some problems in Clairaut's form. So in GATE examination, you just need less than 1 minute to solve this kind of problem. What is the solution? Just put P is equal to A and Q is equal to B. You will get the corresponding solution. So just putting P is equal to A and Q is equal to B, you will get this computation. This is the multiple choice question, so you can directly choose this solution B. So this kind of questions in GATE examination are sometimes selected, and these are very easy to answer. So that's all for this lecture. Thank you for being with us.